Hi, welcome back to Lag Demon Programming and the Compiler Design course. We are about to launch ourselves into the final phase of this compiler course and building a compiler for a language that actually performs actions. It runs and does things that we need to do within our dungeon crawl game. So before we dive into that, though, I wanted to go over a little bit of the overall process of what a compiler does. Now, what we've seen so far is a couple of fairly simple compilers. The first compiler we saw just did simple expressions. It just computed expressions. Then from that, we built up and made a command line parser that just takes very simple command line tokens and fires off commands to our game, such as go to go to a different room, or quit, which is the only two commands I think we have built so far. We'll build some additional commands as well as we get things moving along. The second language that we did is sort of like a data description language. It describes how the dungeon layout is as a series of nested objects of different kinds. And the compiler reads those and builds an object graph out of that file so that things are connected together and you can move around from room to room, and the rooms and the objects are all in the rooms, the items, and so forth. Now we want to build a language that actually does something, that actually computes values and takes actions, interacts with our game and our player and other aspects of the game. So we've already seen parts of this overall compile process. So what I want to show you is the process of what a compiler does and how it works. The first thing that we've already seen, is the Lexical Analyzer. That's a C. So the Lexical Analyzer takes as its input a character stream, or some sort of stream of very, very granular items. It doesn't have to be characters, but for our purposes it is characters coming in. And it outputs a token stream. And that token stream goes to the parser. And we've built a couple of these. These are the YAC files, or Bison files, the .y files. These are the .l files that compile into, using Flex, compile into some C++ code that forms a lexical analyzer. This is the Bison file, or the .y file, that gets compiled into some C++ code that forms the parser. The way this actually works is, get this here, there, that goes that way. The way this actually works is the parser, the lexical analyzer, doesn't do anything with this until the parser asks for a token. When it asks for a token, it starts reading input characters until it comes up with a valid token or an error. If it comes up with a valid token, it passes that token back to the parser. The parser constructs some sort of output, and in our case what it constructs is an abstract syntax tree. So that's the first part of the compilation process, from a character stream to an abstract syntax tree by way of a lexical analyzer and a parser. Now, there's a couple other steps that can go on in here, and one of those steps will come down here a bit, is we'll just refer to it as optimization. There's a lot of different optimizations Optimization. There we go. There's a lot of different kinds of optimizations. There's desugaring that goes on. There's computation of constants together to form a single constant if there's a constant expression that can be pre-computed. And there's performing other kinds of optimizations. We'll be doing a little of that. One of the optimizations we'll probably be doing is a simplified version of type inference. We probably won't be doing full up, algorithmic type inference. We'll just use some simple procedures to identify the type when we can, and otherwise we'll emit an error. And the other thing that this optimization process too does is analyze this syntax tree for errors. In fact, actually, we can break that out as two steps. There's an error check here. An error check here just before that that we'll run, but also when we're like looking for types and stuff, we might generate an error there. And so after the optimization process, we need to emit something. We need to emit executable code of some sort. Now, there's a variety of types of executable code that we could produce. And one of those is executable code for a library or special tool chain called LLVM. Now, the LLVM tool chain is complicated. It's a full up, for high-end professional languages. There's lots of languages that either do run on LLVM or got their start on LLVM and maybe moved on to having their own process. This, I decided after consideration, is too complex to use for this course, and we don't really need it. We're not trying to build a high-efficiency compiler. We're trying to learn about compilers. So instead, I chose a tool called Livejit. Now, this LLVM has a JIT in it, just-in-time compiler, a JIT compiler. Livejit is also a JIT compiler, but this is very much simpler than this. What a JIT compiler is we will emit code that's sort of like assembly language, machine code. We'll emit that code to this Livejit, but it's simplified machine code, and it has some additional features that allow you to build up blocks of machine code for common things without having to write all of the individual statements. And then Livejit is a JIT compiler, so it will actually then goes into its own, the Livejit, we load that into a context in Livejit, and then that context can be executed. I think I have my board here at a bad angle. Let me see here. Yeah, this is more up and down. There we go. There we go. Goes into an execute system for Livejit. This is part of Livejit, this whole thing here. And all we need to do is take our language that we build up and emit this code, this executive code, to Livejit, and then we can run it. The really nice thing about this is, one, it is a JIT, a just-in-time compiler. So it will take our code we emit here and turn it into the actual CPU. It'll turn it into our actual platform code, machine code for our platform. And it only does it once for a particular function or group of code that we write. And then once it's compiled, it stays compiled within the particular run, within the memory. We can also embed this so that this is right inside of our game, which means we can load source code into our game, have the game compile it now with this Livejit, and actually execute it on our CPU as part of our game. And we'll see how that is done. That's the entire compiler process we're going to go through. We've already seen how to build a lexical analyzer, so I'm going to put together very quickly a lexical analyzer. I'll go through it and describe it, and then we'll just start building up our language talking about the parser part. The lexical analyzer is going to be very much the same as all the ones that we built before, with a bunch of keywords, punctuation, and so forth, emitting back tokens. They're all very, very much the same. What's going to be interesting here is the development of the parser and then the development of the abstract syntax tree that becomes our executable code. Once we're done with that abstract syntax tree, then we'll start figuring out how we want to go through optimization processes, what we want to do for analyzing it, and then we'll work on emitting code to Livejit. So that's probably the next here in this video. We can certainly get this done and start on that. Let me see how much time there is. We're only 11 minutes in, so we might get part of this parser built, at least in this video, and then this, I would guess here, the remainder of that, and this is probably another video, and then I'm guessing this will be a couple of videos, probably 2 videos for the optimization stuff, and then the emitting code might be 2 videos. This gets a little bit more complicated, so that's kind of what we're looking for the future here, roughly. This might vary a little bit, but that is the process, and that's kind of the process we're going to go through in this course. So let's get to it and start adding our get our lexical analyzer set up and start working a little bit on our parser. Very careful. Okay. We'll have to do some editing here, obviously. Okay, and here we are, back in Linux and back in our compiler design tutorial project. So, a couple of things we need to do. Hold on, let me adjust my microphone a little bit here. I hope this doesn't make too much noise. All right. Let me first close all these. And we don't need build open. Oh, I was looking at my other screen where I've got some example code that I'm working to. All right, that I wrote specifically for this. So we need a couple of additional things here. So first of all, we need to create a folder for our language. And I've been thinking about this, and I think I'm going to call the language Fungin. And it's our dungeon language. And it's going to be a somewhat functional language with some imperative capabilities. And I'll explain functional versus imperative as we go along, but I'm really much into functional languages, so we're going to try to make this as much of a functional language as we can. So this is going to be our Fungin folder for our project, and now we've got to also include that here. Doesn't really matter too much the order, but we'll do add subdirectory Fungin. Okay, and then in Fungin, of course, we're going to need a CMake lists that's going to contain this basic kind of stuff as well. So let's put that in first. So a new file, it'll be CMake lists.txt, and we'll go to this one. We'll copy all this. We'll change these names in here, and we'll go to here, and this needs to be Fungin Fungin scanner, Fungin parser, This also needs to be fungin. Just make sure we get all these. That's all correct. This needs to be fungin parser and fungin scanner outputs. Okay. So far, so good. Now, I've got a couple of files here we're going to include just to clean up the lexical file that we do. And I'm going to see if I can just drag drop these into this folder. I can. So utils is a set of utilities for working with our lexical analyzer here, and this is the CPP file associated with it. These are the same functions that we have, that we put in our dungeon lexer file. If we go up here, all I did was move them out, and we're gonna ultimately refactor this probably to do these functions here, and I added a few additional functions I think to it, but we don't need to worry about that at the moment. We're just going to separate them out. I had that open. Let me close this. Yeah, we don't want that open. So now what we want is our fungin lexer.l. Let's double check and make sure that that's what I named it. Fungin lexer.l. Yes. Get this. So I don't make any typos here. Under fungin, we're going to create a new file, and we're going to call it that. All right. Here's our lexer. All right. So the usual, we're going to create these sections. This is going to be the top level code section here. Then we're going to have %% and %%, creating our 3 sections. We don't use the bottom section. We do that separately. All right. We need to include our utils up here, and we will definitely need to include the parser.hpp, I believe is what it will come out as. Yeah. All right. Then we also need to go ahead and create that static string buffer that we're going to use. I did not include that in the utils header file because we might want to call it something different in different files. Now, we need better error messages as well. And so better error messages are going to be achieved with this special define that I have here. And this is going to go, yes, this is going to go also in the code section up here. And I'll paste this in and I'll explain it a little bit. It needs to be a design. Let me change this real quick. There might be others. Let me double check. Okay, that's it. All right. What this does is define a special macro that's actually used by our lexer. It gets plugged into it as the YY user action. This YY user action we've redefined for it will give us the line numbers and so forth. We've got to do a couple other things to get that. We're also going to do right under that. Oh, where did I put this? That's why it's not coming out right. I put this in the wrong place. I also put that that out of there. It's got to go in the code section. Also put this in the wrong place. this has to go in the code section. Yeah. And we can just pop it down here below that. That's fine. This is going to help provide us good error messages out of this. That's what it amounts to, in a very automatic way. So right here under the code section, but before this, but outside the code section, we need to set up our options. We've got a couple of options. It's option prefix equals quote fungin underscore. We need that. And we need to do our option no YY wrap. Okay, we've done this before. It's pretty straightforward. Now I've created, because we want to have this system be able to work with different kinds of numbering systems that we might want to use. I've set up some predefined things here. What do you call them? Patterns for our pattern matcher. It's hex, octal, binary, and what it does is it says it's 0, either a small x or a large x. It doesn't care for hex, and then 0 to 9, 0 to 9, A through F, or A through F plus, and it knows it's a hex number. Same with octal and even binary. We can put ones and zeros if we want to. We've got a floating point number, which has got the full up floating point capability, including the e's and so forth in the pattern. Integers, which come after that, because if it finds it's not a float, it'll drop it to an integer. Although this could match, I'll have to check that. Yeah, I'm pretty sure that it'll match this one if it's just an integer. We'll double check that. Symbols are A to Z, A to Z, or underscore plus A to Z 0 to 9 underscore form a symbol. We've got a Boolean true and false in here. This is set up to be a scope operator, and we'll get to that. And we've got a colon and a question mark in here just to make those a little more obvious and visible. Now, I already went over in a previous video using states to create strings and comments. We're going to add an additional one in here for character constants. So I'm going to set up these states. So this is the string state, the character state, the comment, and the block comment and the line comment. And I've already created these as well. And I'll just go over them. I'm going to paste them in and go over everything through the comments. Let me double check here. Copy this. And so here's our string. So a double quote begins a string literal. So we begin the string state and we clear out that buffer, string buffer, by calling that. And then once we're in the string state, that's the only thing we'll pay attention to until we get to that closing quote here. When we get to a closing quote, it will end our processing unless that closing quote is escaped. You'll see here if we've got a slant quote, it'll let the quote be part of the string. Same with I did the same thing with characters. The only difference is you're only allowed one character or these slash symbols to produce those, or the octal and so forth, or a single quote which can be slashed in there, or a double quote rather, and a slash single quote is also, and of course a slash dot and slant in. Actually, if it finds an actual carriage return in, it generates an error. And I'll show you how that happens. Actually, I'm not sure we need to return that error that way, but we'll get to that. And then, of course, there's a regular block comment and line comment just like before. So far, so good. So then we need to process the hex numbers. So what we're going to do is the various kinds of literal numbers to process. So we've got hex, octal, and so forth, and they return these tokens. Int value, in all cases. These hex, octal, binary, and int all return an int. Float, of course, returns a float, and bool returns a bool. And we've already got character and string returning. So those are our types that we'll be working with. And now we've got a bunch of keywords. So I'm going to come back to this. I'm going to put the end stuff in here so that we have it as part of the file, and we're going to work between them. Okay, and the end stuff is end of line and how it handles that. That's what alters the location lines and the location step. Tab or space moves the step inward, and that tells us where it is. This generates an error if anything else came through, and of course end of file returns 0, the 0 token. So we're going to be adding stuff in here as we move along. So let's now take a look at our parser. So there's a variety of things we need to add up here at the top. We'll do the same thing. We've got our fungenlexer.l, and let me double check that. It's fungenparser.y. Let's create that file. So we'll go here and new file, fungenparser.y. And same thing, we're going to go %. Go down here, add a % at the beginning of this one, and then our %% and our %%, creating our 3 zones. Of course, we need a production in here for this to work out right. So first thing we need to do is include a bunch of stuff that's going to be important. Though a couple of these we haven't created yet, so I'm going to take them out. I'm going to paste them all in, then I'm going to remove a couple here. I'm going to remove this here and change this to, I'm going to remove this to and change this to NGON. Our fungenparser.hpp, and some stuff that we're going to be dealing with. So we need some real basic stuff here. We'll capture these things. This is the stuff we need to capture. And I'll rename these things. So my I named my example file I was working on a little bit different. I just made up a name. I'm going to change this to, I guess I could, could have copied those, I guess. Okay. And then we need to give it some directives right here after the code block. And we're going to make this fungen and parse trace and parse error verbose. So we should get some good errors out of this. So let's go ahead and begin. Well, we want to put our union in here, and I'm not going to put all of this in. Let me see here. This is all standard stuff. So we'll put this in right here and add this. So we've got an identifier and values, bool values, character values, string values, and so forth. We need tokens. And I think token type, that's a type. We don't want those. I think these will work for us for the moment. So we can get started. So all I've done here is I've created some basic tokens. We'll add in the lexical analyzer stuff for some of these. They're not in there yet, but we should have the values, or don't we? Oh, here they are. Ident opval. Okay. Let's add these typed ones in here. These are our values. So these just, I think I've explained these before, but I'll go through it. These tokens are typed tokens. They have a value that they return along with them. So a float value is an fnum val, a character val, and so forth. And these are the tokens being sent back by our lexical analyzer. And I don't think I need any of those just yet, and we probably could do these. So we'll put these down here too. So this tells the operator precedence for these basic things. Remember, I told you that the lower it is, the higher the glue. So times and divide have a greater glue than plus and minus, but they're all left associative. So, all right, let's start putting our language together a piece at a time. So when we think about what we want to do, well, we want to build a program. That's a good name. That's what we're going to build, a program. And what is a program composed of? Well, it's a program followed by a line, or it's an error. So this little token here is built in to the parser, and if we get an error condition, it'll match that, and that error will tell it a place to kind of rest to bring it to, and say, okay, we parsed an error and here's a match on error. Let's move on, and it'll move on with the parsing, and it'll put out multiple errors. Otherwise, without this here, what would happen is the first time it hits an error, it'll just quit, and you'll get one error, even though you might have 10 in the file. And it's nicer to get all the errors that it can find spit out first, along those lines. So a line, so we've got here a program is a program followed by a line. There's something else that we can do. I like to put a little comment in here that says empty. So the comment doesn't really mean anything, but you notice I got this or in front of here. So technically, if I wanted it to not be empty and just be a program followed by a line, it would have to have at least one line of code. But an empty file can be parsed, and there's reasons for that. Sometimes you have an empty file in your tool chain that's part of something, and you haven't done that yet. It'll see an empty file, and it'll say, okay, that's fine. It just emits nothing. It's an empty file. And that's how we'll set this up. So a program can be empty. And that will actually compile to us. I believe we would set it up to compile to a single NOP instruction if the program is empty. So it would just be a single NOP instruction and then exit. Or it might just be an exit instruction to shut down the program. It would still have to run its pre and post setup and stuff. So the next one that we got to be concerned about is this line. What is a line? So for our purposes, a line is going to be one of two statements. And for the moment, we're just going to have at the top level of the program a let followed by an ident followed by an assign followed by a body. Now remember I said these are terminals, so these are either a keyword like let, or they're something that contains some information like an identifier or a variable or something. Assign is a terminal that is an equals sign, and then a body. Or it can be a let followed by an ident followed by a param list followed by an assign followed by a body. And that's all any particular line can be in our program for now. We might come up with some other constructs like specialized types and stuff as we move along. But for the moment, let's make some let statements. We'll make our program be some let statements. And we'll have a way of determining that one of them is kind of the entry point to our program, the where it starts executing. And we'll get to that. So in here, the next thing we have to be concerned about is this body and what a body is. So a body is the body of some function, and it can be a line. So this is where we get into the concept of recursion, right? Oops. It can be a line. Or we'll make it an O brace followed by a statement list followed by a C brace. So what is this saying? That the body of a function can either be a line, it can be one of these, it can be a let assignment, or it can be a C brace followed by a statement list. And a statement list we'll define in a moment. There's one other thing that a line can be. Line. Oh, you know what? I got this wrong. This is here. I'm sorry. This is a let statement. And a line can be a let statement or a so this is a function call, or it can be an expression. We'll get to defining those in a moment. So a line is one of these. It's a let statement, a function call, or an expression. That's how we will get our entry point, is if there's one, whatever the first function in the file or the last function in the file, we'll decide that. Will end up being the entry point function. It'll execute it right off the bat. Or it can be an expression. So that a let statement body can be a line, which is possibly an expression. So this could be as simple as an ident followed by an expression, which could be a single value or something more mathematical, or identifiers and so forth. All right. And I know this kind of top-down language design can be a little bit confusing, but once we get it all written, we'll be able to walk kind of backwards through it and see how the language works and see how we're specifying it. And you'll notice, too, this is a little bit different thinking process than our data description language or our command processing language, which was fairly simple. So now we have to get into a thing called lvalues and rvalues. And I'm going to explain those. What I'm going to do is set those up here. Actually, we still have to do, we've got a let statement body, statement list. We need to do a statement list first. So a statement list is pretty straightforward. There's a statement list is a line or a statement list followed by a line. Okay, so this is just saying that we can have these kinds of statements, whatever they may be, a let statement, a function call, or an expression. We can have a list of them one after another, and we'll encode that as some kind of a list. Now is when we have to get into the idea of lvalues and rvalues. So if you think about an assignment, where you're going to take a value and say like a equals 3. Okay, that is an equality. In mathematics, that says that the two are one in the same. So we call the thing on the left of the equal sign an L value, or left value. It gets a little more technical than that, but that's a good way to remember it. The L value must be a symbol. It must be an identifier of something that has a location in memory that we can store a value in. The R value, the one on the right-hand side, does not have to have a storage location. It does not have to be a symbol. It can be a symbol, or it can be a literal value, like a 3, or a string, or a character in single quotes. An R value is something that's retrievable. It's either an immediate value, a literal value, or it's something that can be looked up as a variable, as something that sits in a storage location. So an R value can be an L value, or in other words, no, an L value can be sitting in an R value, but it's still an R value when it's on the right-hand side. So it can be a symbol. So an L value is always an identifier. So what we're going to do is say L value, and we're just going to say it's an identifier. And we're going to have a special way of determining what an identifier is. And an R value, we're going to say it can be an L value, that's fine, or it can be a literal value, a literal. Okay? So that's exactly what I just described. An R value can be an L value or a literal, but an L value must be an identifier, which means an R value can also be an identifier. That's what this is describing. Since this can be an L value, and an L value can be an identifier, this can be an identifier. This cannot be a literal. You can't assign anything to a literal. You can't say 3 equals B in programming. And it's kind of an obtuse thing. It's a legally correct thing with equality concept in math to say 3 equals A, although most mathematicians would say turn it around. Say A equals 3. It just sounds better than 3 equals A. Okay, so we've got L values and R values. Now we need to define a literal. So literals are going to be our string val, or an int val, or a float val, or a char val, or a bool val. And that's what we have for literals. Now we got to create a couple of things. We got to create a R value list, because an R value can also be the arguments to a function call. They would still, this is why it's not entirely true that R values are the stuff on the right hand side of the equals sign. I said that it's kind of like that. It's technically not exactly the same. An R value is always something you can retrieve the value of. An L value is something that you can store a value into. But R values are not something you can store into, even though an L value may be acting like that. Okay? And yeah, that's close. You'll see better how it works as you see the dynamics of how things operate. And I'll continue to find better ways to explain such things. We do get a little bit technical in this. So let's create an R value list. And again, it's just this recursive concept. It can be an R value, a single R value, or it can be an R value list followed by an R value. Oops. And then we need a function call. So we'll just call it fun call. So I'm going to write this. I'm going to say it can be an ident followed by a unit. Actually, we can say, well, that would be deviating from my notes, and I don't want to do that right now. And I'll explain what a unit is when we get to it. Ident followed by an R value list, or it can be an open parent followed by a fun call followed by a C parent. So basically what this is saying is that these can look like this. It can look like my fun A, my fun with this, or it can look like that would be that one. Let's move it down to here. This is what these would look like. All right. Or it could be my fun A3, A2, 4.5. Okay, that would be an R value list. Or it can be something like this. My fun A, B, C. That would also be valid function call. You notice we don't enclose the parameters here in parentheses. These two parentheses together form a concept called unit, and we'll get to that. In functional programming, unit just means nothing. There's nothing being passed into this function. That depends on how the function is defined. If it doesn't take any parameters, then it probably needs to be told it takes a unit. And we'll also have the idea in here at some point in time about specifying a return value, a return type, but I'm not going to do that just yet. We'll make this work without that. It'll infer the return type based on the return expression. Okay. Now we've got this thing called an expression. And this gets more complicated. So we probably will need to go back. First of all, we need to take a look at our Lexer. I only did these. We've got more that we need to do. We need to put in the keywords and the operators. Let's go back to, let's copy this. So we got that, and we don't have, okay, we don't have the keywords, or these, or these, or these, or this. So we need all of this, and then we need to include all those keys. So I'm going to put this in here. I'm going to copy this in. So this is the keywords that we're going to use for now. We'll have more keywords in the future, I'm sure. But then these are the symbols that we're going to use, at least for now. Well, we won't get to these other fancy operators just yet. We're going to work on the basic ones, but I'll put them in there for now so that we have them and we have all the tokens. Now let me go back and get all the tokens in here properly, because I didn't put them all in before, and I probably should have. So let me go back up here to our tokens. Well, part of the reasons I didn't put, yeah, I can't put the typing stuff in just yet. That's fine though, but we can put the tokens in. And I need this. Oh, I actually only need this, I think. I'll put these here. Float. We don't need to worry about those yet. We don't have that stuff yet for typing them. We'll have to build the abstract syntax tree before we can set all the types. However, we have type here. Oh, yeah, these are the actual type keys. And how did I define types? Oh, yeah. All right. Let's continue on. This might not be quite compilable yet. Let's get the rest of this in place. We need to do this expression piece. So let me do this down to here. Oops. I messed that up. here's our expressions. You need to put a semicolon there. So these are all the types of basic expressions we'll work with. An R value on the right can be an expression. And we can have an expression plus an expression by specifying R value here, we pick up everything it could be, right? An L value or a literal, which is an identifier, or any of these. So, and then we've got the plus, minus, divide, equal, not, less than, greater than, so forth. And increment and decrement operators, function calls, and expressions. And a function call is an expression which can be wrapped in this. So I wonder why. It seems to me that I had to do this. That's not good. It seems to me that I had to do this. I'm going to take these out. We don't need that there. That's going to be, oops. When I was experimenting with it, I seemed to have this for it to pick up that a function call could be wrapped there, even though I had a function call as an expression and an expression can be wrapped in them. It didn't seem to like it. So now we've just got a few more. Yep. We've got a few more constructs to put together here. A param. So a parameter, a param, or a parameter is something that you put in a function definition, and it tells the compiler that this accepts certain things, types that are used inside the function body. Arguments are things you pass into it. So in a way, parameters are a type of thing like that. That's an identifier in this case, or it's a typed identifier, and I'll explain that in a moment. We'll show you what a typed identifier is, the syntax for it. So that's a parameter. We need a parameter list, which is a parameter, or a param list followed by a parameter. That creates a list with that recursive method I told you about. And then we have a typed identifier. And a typed identifier is going to be this. It's going to be an open parentheses followed by an identifier, followed by a colon, followed by a type, followed by a cparen. And that's all it is. That's a typed identifier. And then we've got identifier. And that's this ident. And that's all it is. And finally, we have this thing called a type. And we have to put these in. It's going to be int t or float t or string t, and I added the t on the end because these are not literal values. These are type definitions, so they represent the literal word, float, string, character as a keyword. We have byte, we have bool t, and we're eventually going to use record and an enum to build out our system. And finally, we have this thing called unit, and I promised I would explain that. And it's simply O paren, C paren, and that's it. All right, that's our language. And you might be wondering, what does this language look like? And so I will show you, but first I think there's a little thing I need to fix here. This, we can't just yet call that type because we don't have type defined, and we're going to do that in the next video because this video has already gone long. We're already at almost an hour. So I'm going to give it a whack and see if it builds. It probably isn't going to build. What doesn't it like here? Oh, I did this, add library. This needed to be fungin. And we're getting some errors. Let's see here. Real quick, maybe we can fix this. Ident is used but is not defined. Indent. This was supposed to be ident. Funcal loc last line. Oh, this needs to be fungin. This probably should be fungin. This needed to be fungin. Okay, what do we got happening now? Okay, we got some more of this problem here. I missed a whole bunch of them. So what we'll do is we'll go here. This is all okay. UNGON. Let's copy that. Hopefully I won't miss any this time. I don't know why I didn't see all those. So I just made up the word when I was doing the testing and figuring out how I wanted to build the language. I called the language Funkel because I couldn't think of anything else. So I've got Funkel all over the place in my example code that I've been copying from. So let's see if this fixes it. Nope. There's more Funkel hanging out. Where? Where is it all? At? Oh, it's here. Let's copy. This is the lval. Let's just do this. And this, and this, and this, and this. See if I can catch any more. This is fungin, lloc. This is supposed to be lval. This is fungin lval. All right, let's try it. Obviously missed a few. I probably could have done a find and replace, but I went down this route. I didn't think there were this many. Only one left. What do you know? Where is it? Fungin. Ah, it compiled. What do you know? So I'll show you real quickly what it looks like with an example file here. I'm gonna bring it over here, then rename it. I'll drop it right into this folder with it, and then I'm gonna rename it to FNG. This is the kind of stuff that will compile. Let function, a int, 1 plus 2 plus 3, so forth. It can compile that. So let's real quick test. Remember what I said about if we don't get any errors, right, we're good to go. So this is static. This should be statically linking with game. If we go into main, actually, yeah, I'm going to wait for another video to test it, but it compiled, so I'm pretty confident in it, and especially because I've run it already. In the next video, we'll test it out. Actually, it might be 2 videos down. This might, well, it would be the next from this video. This video was going to get turned into 2 videos because it's over an hour long. So we'll, yeah, that's it for this video. We'll see you in the next video. Thanks for watching. I hope you liked it. If you liked it, hit that like button. If you really liked it, hit that subscribe button. And I'll see you in the next video.